Hi, it's Russ Moan here from InPlay to present to you some of our capabilities for RF tests that come with our NanoBeacon evaluation kit and our NanoBeacon Config Tool software. So here I have our evaluation kit. There's a programmer board and one of the sample devices connected together, and they're being powered by this USB cable connected to the PC. And I've started up the NanoBeacon Config Tool here on the left-hand monitor. I will probe for the correct UART. It's come up as COM4, and I'll connect to the device. So it says IN100 connect, successfully connected, okay. And it starts up in this advertising tab. And what I want to present today is going to be under this RF test tab. So for the sake of viewing, I'm going to push this basically this coaxial cable that's connected to our spectrum analyzer behind the monitors. So the spectrum analyzer screen is shown here on the right-hand monitor. And the first thing I want to demonstrate is how there are internal capacitors inside of the IN100 which are used to trim the 32 megahertz crystal to be exactly essentially 32.000 within some less than, let's say, 20 ppm accuracy. So to see the effect of this internal capacitor code, which essentially trims the crystal oscillation frequency, the 26 megahertz crystal oscillation frequency, we're going to use a carrier test. So the carrier test section is right here. I've got 2.402 gigahertz selected, and I will hit start test, and you can see essentially one tone has come out of the spectrum analyzer. So the span is very narrow here, and it's 1 megahertz. So each of these vertical lines represents 100 kilohertz, and the resolution bandwidth is quite low as well. It's 1 kilohertz. So we're looking with a pretty fine filter at the frequency resolution of the tone coming out of here. And you can see if I do a peak search, the actual frequency is 2.402.014 gigahertz. And the screen is centered perfectly at 2.402. So you can see it's a little bit higher than the ideal value. And these internal capacitor codes, they actually represent how much capacitance is being used as the load capacitance on either side of the crystal inside of the chip. And they can be 0 through 15 integer. Each value basically steps up the load capacitance by 1 picofarad seen single-ended, or if you view that differentially, it's a half picofarad. So if the CL spec for this particular crystal is 8 picofarads, or let's say 7 picofarads, we know a capacitor code of roughly 14 or 13 would probably be appropriate, because it also has to include the board parasitic capacitance, the pin parasitic capacitance, and any other parasitics that usually total up about 1 picofarad. So it's set at 6 right now, and it's a little high. So to reduce the frequency, I'm going to increase the capacitance. So I'll go from 6 to 8, and then I'll press apply. And you can see indeed the tone has moved below the 2.402 gigahertz mark in the center. And how much below? You can see it's about 2401978. So about 22 kilohertz below. And let's see if we can do better by trying 7. So 7 for the capacitor code brings us as close as we're going to get to the ideal frequency. So it's 2401995. So it's about 5 kilohertz shy of ideal, and that's well within the ppm errors put forth by the Bluetooth SIG for carrier frequency accuracy. Thank you.